We have a solid-state light source that meets the demands of many applications that have needs that have not been met by other solid-state light sources like LEDs and lasers, specifically visible LEDs and visible lasers. Solid-state light sources are very good because they save energy, number one. They are green technology. They replace the lamps that consume too much power, and they have short lifetime. Solid-state light sources, they have lifetime that they can last very long lifetime. They can last for 20 years. And also they consume much less power. So that's really the key advantage of solid-state light sources. Our light source has key advantages over LEDs and lasers in terms of efficiency and number two of cost. And also it has some characteristics that can be designed to meet some applications. Some of these applications that like projection systems, specifically cinema projectors, and number two, like headlamps in cars and other automotive applications. These have certain demands that have not been met by LEDs or lasers, and our light source meet these demands. Our optical cavity consists of three parts. One is a cylinder that has reflective side walls inside, or mirror in other words. And also we have phosphor on top of a mirror, and we have a top side that has an opening in it. It's a mirror that has an opening in it. So to form a cavity, we put our cylinder here, and then we close it with the top part that has an opening in it. So in this case, light will go through the opening, the violet light, which hits the phosphor, gets converted to green, and the green exits only from the same opening. Now we have a laser light source here, a violet or blue light source, and you see the violet is going through, and it has a speckle in it, which is not good. Now we add our optical module to create the green light source. Here's our optical module. Then we bring the phosphor that's with the mirror here, and we create our cavity. And by closing this cavity now, you could see that we generated a green light. So you have blue light going in. If you look here, it's a blue light. And here it's the same thing, blue light. This mirror allows the blue light to go through, but this mirror reflects the green toward me. So we created actually a green light source with no speckle in it, which is good for displays. That's another big advantage. Now, one of the key advantages for our application is that you can couple more light into it, which means that you can add more lasers and then get more light. This, like LEDs, cannot do that for certain applications, like projectors. If you add actually more LEDs, the light will be wasted because it cannot get into the screen. That's why cinema projectors, for example, till today, they use lamps. They cannot use LEDs. Even though if you combine 100 LEDs together, they can actually generate light that satisfies cinema projectors. But that doesn't work because that light will be wasted and it will never get to the screen. In our light source, this is different because you can add more lasers in an array like this one here that has 24 lasers. For example, they can be coupled by optics to go to our light source or our cavity here, and then generate again the same size cavity. And in this case here, you see that you have another green light source. But in this case, you're adding more power in this case. Our light source is low cost compared to lasers, and also it's scalable, which means that depending on how much light you want, you can scale this light source. LEDs are not scalable. For many applications that we are addressing, if you add more LEDs, the light is wasted, cannot get to the screen. In our case, it's the opposite. As you add more lasers, you get all the light to the screen. So our light is scalable and low cost at the same time. And also it saves energy, which means it's low power. And in addition to that, it's actually long lifetime, 60,000 hours of time life, compared to 500 hours of lamps that are currently used in projection systems or cinema projectors.